Alright, so we have worked with log and exponential functions, and now we're going to start solving them. So we're going to start out solving exponential functions, and we're going to start out with exponential functions that have the same base. So I want to solve 2 to the x plus 1 equals 2 to the 3x. Okay. So I want to think about this for a second. So if I have b to the x equals b to the y, this can only be true with a one-to-one function if x equals y. So this is true if and only if x is equal to y. Okay? So if that's the case, then that means that I have 2 to a power equals 2 to a power, and that means my powers must be equal. So I get x plus 1 equals 3x. So if I move this x out of this side, I get 2x equals 1, so my x is 1/2. Alright, so if my bases are equal, then I can just set the two powers equal to each other. Alright, so let me take it a step further. If I have 25 to the x equals 5 to the 3x plus 2. Now this time I don't have the same base, but I do know that 25 is a power of 5. So I could write this as 5 squared, and then I write times the x that was already there equals 5 to the 3x plus 2. And now I can set my powers equal to each other because I have 5 to a power equals 5 to a power, so that must mean that 2x equals 3x plus 2. So if I move some stuff around, I move my 2x over here, I get x equals -2 when I move that to this side. So those are my answers for those two problems. Now, as long as I haven't done something wrong algebraically, those should be solutions because I'm starting out with an exponential function which doesn't have any kind of domain restriction on it. So let me do one more that's maybe just slightly more complicated. I have 8 to the x plus 2 equals 16 to the x plus 1. Now I know that it might be tempting to think that 8 or 16 is a power of 8, but it's actually not, right? 8 times 2 is 16, 8 squared is 64. So these aren't really powers of each other, but I do notice that 8 could be written as 2 cubed. So I could write this as 2 cubed times x plus 2 in parentheses equals 2 to the 4th is 16 times x plus 1. And so I end up with 2 to a power equals 2 to a power. My powers must be equal, so let me write them and distribute at the same time. This would be 3x plus 6 equals 4x plus 4. I can move my 3x. I get x equals, and then I subtract 4 over here, and I get x equals 2. There we go. So those are my 3 examples with the same bases. Alright, so let's pull out a different type of equation. What happens when we don't have the same base anymore? So now at this time I have 5 to the x plus 2 equals 4 to the x. Now this time I can't write 5 as a power of 4, and I can't write 4 as a power of 5. So now I need to use a different thing. So this is where we need our log rules. I want to solve for an x and it's floating in the air. Okay, so I need to be able to pull it down, and with log rules I can actually pull down those exponents. So that's what I want to do. Now technically speaking, I could use any log base anything to do this with, but I want to use one that my calculator knows. So I either want to use log, L-O-G, or ln. Now I'm kind of partial to ln, and the math department is too, so I'm going to just take the natural log of both sides. But if you take the log of both sides, you'll still get the same answer too. I'm going to use the natural log of 5 to the x plus 2 equals the natural log of 4 to the x. And now our power rule says we can pull down this exponent into the front and write it as x plus 2 with parentheses times ln 5 equals x ln 4. Alright, I need to solve for x here, and I have x in these set of parentheses. So I think what I want to do here is distribute. I have x ln 5 plus 2 ln 5, right? I'm just distributing here and here, equals x ln 4. And then just like when we were solving those crazy inverse functions, we had x, right? I have x over here, And so I can move my x's to the same side and factor them out. So this one's going to go over here. This one's going to come to this side. So I have x ln 5 minus x ln 4 equals negative 2 ln 5. I can factor out my x here. Write ln 5 minus ln 4 equals negative 2 ln 5. All right, I'm just going to divide by this whole thing here. ln 5 minus ln 4 over here is the same. And there's my answer. Okay, now this is the most exact answer I'm going to get. If I can put this in my calculator and get an approximation, but I would have to round it to approximately 3 decimal places. Now, these answers can be displayed like in a million different ways, because I could change this negative 2 natural log of 5 to the natural log of 5 to the negative 2, or I could write that as the natural log of 1 over 25, right? So it's the same thing. Either one of these is equivalent for the top. And then on the bottom, I could use my quotient rule if I wanted to and write the natural log of 5 over 4. Do I have to do that? No, I don't. It's the same answer. So, but I'm just telling you that it could be in lots of different ways. Okay, so let me do one more of those. I have 2 to the x equals 3 to the x plus 1. And so this gives me the natural log of 2 to the x equals the natural log of 3 to the x plus 1. I can bring down my x. I'll bring down my x plus 1 on this side. I'm going to distribute my ln 3, x ln 3 plus ln 3. And then I'm going to move this x to this side, so I get x ln 2 minus x ln 3 equals the natural log of 3. And I can factor out my x. So this is natural log of 2 minus the natural log of 3 equals the natural log of 3, and then I can just divide. So this is the natural log of 2 minus the natural log of 3. Again, I could write this bottom as the natural log of 2 divided by 3 as one natural log in the denominator. I don't have to. I can put this in my calculator. It gives me the same answer. Alright, so let's move on to one more type that I want to do. And so these look more like when we were doing our PERT, you know, like the continuous growth sort of equations. And so this time I only have one exponential function, right? I just have the one thing with the exponent on it. So what I want to do in a case like this is to solve for it's kind of like when we were doing absolute value. I just want to solve for this e to the 2t. So that means I'm going to divide both sides by 10. This is going to give me 20 equals e to the 2t. And now on those the previous exercises, I didn't really have to use ln. I could have used log. But this time, since I'm dealing with e directly, I definitely want to use the natural log of both sides. So natural log of 20 equals the natural log of e to the 2t. And I am going to then just simplify this side. It just becomes 2t equals ln 20. And I divide by 2, and there's my t. All right, so let me just do one more of those. I have 3 plus e to the 2t equals 7e to the 2t. So these e to the 2t's, they're actually like terms. So I want to get them both on the same side. So I have 3 equals 7e to the 2t minus e to the 2t. Now if I had 7x minus x, this would be 6x. So that's exactly what this is, 6e to the 2t. Now I have a problem just like up here, where I want to isolate the 2t, or I should say e to the 2t. And so I'm going to divide both by 6. I get a half equals e to the 2t. I take the natural log of both sides, and really all I get on this side is 2t, because the natural log of e to the 2t is 2t, and I divide by 2. And there's my answer in its exact form. Alright, so let me just do one more interesting problem. It's just like factoring never dies. Alright, so if I have e to the 2x minus e to the x equals 12, this should look, you know, like a quadratic. So what we do with a quadratic is move everything to one side and try to factor it. So just a reminder on our exponent rules. If I have e to the x times e to the x, that's e to the 2x, right? That's where I can add my exponents. So this e to the 2x is really like e to the x times e to the x. So when I go to factor here, I can think of this as e to the x times e to the x. It's just like x squared. It's just e to the instead. So now in my middle, so like to get negative 12, that would be negative 4 plus 3 to get me the negative in the middle, right? So I'm going to have minus 4 minus 3 equals 0. Just like anything, when I have two things multiplied together that give me 0, I can set them each equal to 0 separately. And now I have just a simple exponential function, e to the x equals 4. I take the natural log of both sides, and I get x equals the natural log of 4. That's a perfectly legitimate answer. So now if I try to set, oops, this should be plus 3, right? I put them both in as minus. So if I have e to the x plus 3 equals 0, I have e to the x equals negative 3. And I can stop right there because there's no way that I can raise a positive base to an exponent and get a negative number. I can raise it to negative exponents, but then I just get a really small number. I never get a negative number out of it. So this one doesn't give me a solution. And so this is my only one. All right, so that was solving different types of exponential functions. Next time it will be logarithmic.